Okay. Now I'll share the screen once again. Right. For irreversible processes, I have covered. Right. Right. Wait. Just wait. Okay. Fine. Right. So up to this part we have covered. So we are covering Clausius inequality. It says that for a cycle, the cyclic integration dq by t is always less than equal to 0. For reversible processes, if these processes are reversible, that means they can return to their original or initial position on itself. So reversible. The processes are reversible, integration dq by t is equal to 0. For irreversible processes, integration dq by t will be less than 0. Okay. But what is this q by t? What is this q by t ratio? This q by t ratio is termed as entropy. It's termed as entropy. Now, what is entropy? See, entropy has a wide meaning in different areas. Entropy is used in engineering. Entropy is used in mythology. Entropy is used in astronomy. And entropy is used everywhere. Okay. What is entropy? That we have to understand. Okay. So the classic definition for entropy is degree of randomness, right? So I will give a very simple example for your understanding. That example will give you idea about what is entropy. See, suppose there is a jar of water is there, or the I have a vessel, okay, bucket I have filled with water, right? Initially, let us say its temperature is 30 degrees Celsius. Now I have kept it on a stove, okay. So there is a flames are there, and its temperature will increase, right? Now, as its temperature reaches to 100 degrees Celsius, or its temperature increases, suppose from 30 to 80 degrees Celsius, right? What happens to the surface of the water? Is it still, or is there any movement in the water? Yes. So initially water was very still. एकदम शांत पाणी होतं, एकदम स्टेबल वॉटर होतं 30 डिग्री सेल्सिअस मध्ये. जसं जसं मी टेम्परेचर वाढवली, if I reach to temperature let us say 80 degrees Celsius, what will happen to the water? We will observe a minute vibrations in the water. आपल्याला असं वाटेल की पाणी उडायला लागले. And when it reaches to 100 degrees Celsius or above, we'll see, literally see, the surface of the water is dancing, right? आपल्याला एकदम ते भांड्याचा आवाज लागतो तर 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 आतल्या वॉटर मधून आपले व्हायब्रेशन दिसायला लागतात, जाणवायला लागतात. त्यातनं बबल्स फॉर्मेशन होतात, बऱ्याचशा गोष्टी त्यामध्ये तयार होतात. नाव सी, मी फक्त काय केलं या केसमध्ये, मी फक्त आय हॅव जस्ट इन्क्रीज द टेम्परेचर. बट व्हॉट अबाउट द मूवमेंट ऑफ पार्टिकल्स, हाऊ इट ऑकर्ड, राईट? So all this movement of particle, vibration, translation, acceleration movement, which is happening due to increase in temperature or due to transfer of heat, that we are terming it as a entropy. That we are terming it as a entropy. Okay. So with the heat transfer, we observe some randomness in the structure, vibrations, movements in the substances. That vibration, that movement, that randomness, what we are terming it as a entropy. And next statement is very important. Entropy is a property of system. Is a property of system. Entropy is a property of system. What does that mean? That means I can say that at state 1 I have entropy, let us say S1. At state 2 I can say I have entropy S2. This is possible only for properties. Opposite to that, we have heat and work. Heat and work are not properties of the system. That is why we cannot say at state 1 we have heat 1 and state 2 we have heat 2. We cannot say, because it is not a property of system. But entropy or temperature, these are the property of system. That is why I can say at state 1 I have entropy S1, state 2 I have entropy S2. Is it clear? Entropy is the degree of randomness. Okay. Now, what about processes, right? This we have studied about the cycles. What about processes? Now, next I will draw a process. Let us say I have P versus V chart. Initially, oh, we are at state 1. Okay. Now, slowly, a process takes place and it reaches to state 2. Okay. What about entropy change in this process? So, for this, we have a statement or a rule that integration dq by t is always greater than 0. Okay. Integration dq by t is greater than equal to 0. Okay. So previously, write down this part first. Write down this for the cycle, and then we can go for the processes. Okay. Write down Clausius inequality. Yes, completed. Okay, we'll move to the next one. So we are at this PV chart, pressure versus volume chart. So initially it was at state 1. Again, we move towards the state 2. Okay. So process takes place, and this is the path. Now for processes, there's a correction. DS, change in entropy. Now observe here, I have written DS, not delta, because this is a property of system, so that I can write it as a DS. Will be always greater than or equal to integration del Q by T. Okay. So for cycles, we have this law, integration, this one, dq by t is less than equal to 0. For processes, what is happening to this? I don't know. Wait. I don't know why. Okay. 1. Again, I will draw 2. For processes, change in entropy is always greater than equal to integration dq by t. Okay. So in this, if the process is reversible, so for reversible process, in this case, change in entropy will be equal to integration del q by t. Okay. Or I can say that in this case, all the change in entropy. So if I take the integration, sorry, this is again integration here, integration. So here integration, if I take in this case 1 to 2, so this will be S2 minus S1 will be equal to integration del Q by T. So this is for only reversible process. Okay. What about irreversible? For irreversible processes, this integration ds is always greater than integration dq by t. Okay. Now, if I want to make it equal, I have to add some quantity here. Then I can make this RHS equal to LHS, right? Now, if I take integration here, what will the integration here again? So this will be S2 minus S1. If I take from 1 to 2, will be greater than integration dq by t and plus some constant. Okay. Now, if I want to make this equation equal, so I have to add a quantity. So that is, no, not now, equal to integration dq by t plus some constant. And this constant, what we are written it as a S generation. What is S generation? S generation is entropy of generation. Okay. So see here, for irreversible process, integration ds is greater than dq by t, or s2 minus s1 greater than integration dq by t. If I want to make it equal, I have to add a constant on RHS that I have added. This constant we are referring it as Sgen. Sgen is nothing but the entropy of generation. So this is again very important equation I'm going to write. S2 minus S1, that is change in entropy, will be equal to integration dq by t plus S generation. This is again very important equation in order to solve the numericals. Changing entropy is equal to integration dq by t plus S generation. Okay, write it down. Yes, written. Now let us talk about entropy of generation. Okay, this is very again important topic. Entropy of generation, or what we call it as a S-gen. Okay. Now, from equation you can see that the change in entropy. So that is, let us say previously this entropy was S1, final entropy S2. This change in entropy is integration dq by t. Okay. So whatever heat transfer takes place in this process Q, you take Q1 divided by T1 minus Q2 divided by T2. That integration plus some constant. Okay, plus some constant. And this constant we are referring as the entropy of generation. That means during a process entropy, there is some increase in the entropy. Okay, there is always a increase in the entropy, and that entropy we are calling it as the entropy of generation. And there is a law of entropy of generation which states that during irreversible processes, the entropy always increases. And as all the processes in the universe are irreversible, the entropy of the universe is constantly increasing. Understood? So for see, if we are going with the reversible processes, then there is no entropy generation. All the what is the change in the entropy is just integration dq by t. But if you are going with irreversible processes, there is a extra term is added, that is entropy of generation. And we can say during irreversible processes, the entropy always increases. Why always increases? Because this S generation term is always greater than 0. So for, we can say, for reversible processes, this S generation is 0. That is why we are getting this equation, S2 minus S1 integration dq by t. And for irreversible, S generation is always greater than equal or greater than 0. Okay, so as S generation is always greater than 0, we can say that during an irreversible process, entropy always increases. And as all the processes in the universe are irreversible, so we can say that entropy of the universe always increases. Entropy of universe always increases. Okay, so write it down, this part. So very important statement we have just studied, that entropy of the universe always increases. That is, the degree of randomness always increases. So previously I said that entropy is the concept which is used, not only used in engineering, but it is also used in the mythology or philosophy, etc. फिलॉसॉफी मध्ये आपण बघतो की आपली इंडियन फिलॉसॉफी किंवा मायथॉलॉजी आहे ती काय म्हणते की ते 4 प्रकारचे युग असतात. म्हणजे आतापर्यंत झाले, सतयुग, त्रेतायुग, द्वापर युग, आता चालू आहे ते कलियुग. तर त्यामध्ये ते देखील ते असं म्हणतात की एंट्रॉपी हॅज इन्क्रीज विथ एव्हरी युग. म्हणजे जेवढी एंट्रॉपी सतयुगात होती त्यापेक्षा जास्त वाढली त्रेतायुगात, त्यापेक्षा जास्त वाढली द्वापर युगात, आणि त्यापेक्षा सगळ्यात जास्त एंट्रॉपी आता आपण म्हणू शकतो की कलियुगात आहे. So that is what it means, that people are becoming unstable. The things, all the society, government, everything is becoming unstable. That is, entropy is increasing. So that is a point of view in the philosophy. If you go with the astronomy, astrophysics, etc., there also they are saying that the universe or the planets, stars, etc., the degree of randomness is increasing. So there are high chances of stars collision, planet collision, etc., etc. So these chances are increasing because all the entropy or the randomness of the universe is increasing. There are high chances of disturbance in the universe. So that is from the astrophysics point of view, and entropy is everywhere. Like this concept is studied by each person, not only engineers. In medicine also they are studying, in astrophysics also they are studying, in other branches or other streams also they are studying. But for us, being mechanical engineer, we are focused on this only, that heat entropy generation always positive. It is associated with heat transfer. For irreversible processes, change in entropy is integration dq by t. For reversible processes, changing entropy is integration dq by t. For irreversible processes, change in entropy is integration dq by t plus S generation. and this H generation is always greater than or equal to 0. For reversible processes, this is equal to 0. For irreversible processes, H generation is always greater than 0. That means entropy is always increasing. Okay, so we'll solve one numerical here and then we'll see next theoretical part. Okay. Okay. So this is related to Clausius inequality. Let us see if you can solve it. So figure below shows a reversible heat engine ER having heat interaction with three constant temperature systems. Calculate the thermal efficiency of the heat engine. Okay. Now see here, there are three heat sources are there. Heat sources we have studied. Thermal energy reservoir, which is a higher temperature. Three sources are there, and there is only one sink somewhere here. So here in this case, they have given three heat interactions. So there is a one heat engine is there, which receives heat from three sources, and it does some work. So it receives heat from these two sources, Q1 and Q2. It does some work and it releases the Q3 amount of heat. Okay. So in this case, we have to find its thermal efficiency. So for this, we have to make use of Clausius inequality, right? How? Because in this case, Q3 is unknown. Without knowing Q3, we cannot know heat interactions. Without knowing heat interactions, we cannot calculate thermal efficiency, right? So I will write down given data. Pay attention. So here T1 is given 1000 Kelvin and Q1 is given 100 kilojoule. T2 is given 500 Kelvin. Q2 is given 50 kilojoule. T3 is given 300 Kelvin and Q3 is unknown, right? W is also unknown and we have to find out thermal efficiency. Now, what is the formula of thermal efficiency? We have studied in last lecture is equal to net work output divided by heat input, right? In this case, this net work output is unknown that we have to calculate. Again, this QH is unknown. What is QH here? QH will be all heat received. No, it is known actually. QH is all heat received will be equal to Q1 plus Q2. So we can say this is 100 plus 50 will be equal to 150 kilojoule. So that is QH, that is heat received. What about W? So W, in order to calculate W, W will be calculated will be equal to all the heat received minus all the heat lost. So that will be equal to net work done. Net work done. Okay. Again, in this case, QL, that is heat loss is in this case is Q3, which is unknown. Now, how to calculate Q3, right? For this, we have to make use of Clausius inequality. So see here, this is reversible heat engine, right? Heat engine, in this case, we can say it is a cycle process. So we can write it as an integration dq by t equal to 0, or I can say q1 divided by t1 plus q2 divided by t2 plus q3 divided by t3 will be equal to 0. Okay. So see here q1 is given 100 kilojoule divided by T1 is 1000 Kelvin. So I will convert kilojoule into joule by multiplying it by 1000 plus Q2 is 50. So 50 into 10 to power 3 divided by 500 Kelvin plus Q3 is unknown divided by 300 will be equal to 0. Okay. So can you calculate Q3 from these equations? Can you calculate Q3? So here I will cancel 1000 to 1000. So this will be 100. Again, plus I will cancel this 500. with this. So this will become how much? 50 into this will become 100 plus Q3 divided by 300 equal to 0. So calculate Q3. Calculate Q3. Just calculate Q3. And by calculating Q3, calculate the thermal efficiency. So actually I'm searching for more numericals because more you solve, more your concepts will be clear. Yes, anybody has calculated? Minus 60. Yes, correct. Minus 60 into 10 to power 3. So it is coming minus. Why minus? Because it is a heat loss. Okay. As it is a heat loss, it will be minus. Okay. So this will be in joules. Now next calculate the thermal efficiency, right? So in this case, what will be the W value? So I'll go to the next page. Okay, the spaces are limited here. So W will be here. QH I have calculated. How much QH I have calculated? 150 kilojoule or 150 into 10 to power minus 3 minus QL, that is minus 60 into 10 to power 3. So this will give me W as 90 kilojoule, 90 into 10 to power 3 joules, and put this value in this ratio. So this will become 90 to 10 to power 3 divided by QH is 150 into 10 to power 3. Take the ratio. I think this will become 0.6, right? 0.6. So I can say efficiency is 60%, right? So anybody is successful in calculating efficiency? 0.6. Yes, Avantika, good. Others also calculate. I will explain the numerical once again, don't worry. Yes, others are able to calculate 60% efficiency. Now, see the example here. I will explain what is happening here. Okay. Okay, see, I will explain this example. So here in this case, we had two sources, one is at T1, another at T2. Here we have a sink. So this is a sink and these two are the sources. There is a heat engine which receives the heat. It does some amount of work W and this is the heat loss. So see here, we have to calculate the thermal efficiency, formula thermal efficiency, net work output divided by heat input. Heat input will be equal to Q1 plus Q2. That is the heat received from the sources. So that will be 150. W here it will be heat received minus heat loss. So here heat received we know, but we don't know heat loss. So for that we have to make use of Clausius inequality. What is called Clausius inequality for reversible processes? Integration dq by t equal to 0. So in this case, sorry, integration cyclic integration dq by t equal to 0. So q1 divided by t1 plus q2 divided by t2 plus q3 divided by t3 equal to 0. From this, we have calculated q3 as minus 60 kilojoule. So I have put this value here again. I have calculated w. By calculating w, I have calculated thermal efficiency. Okay, so write down this problem. Very, very important problem. Okay. So I will include some numericals. Just I am transferring through Bluetooth. I will try to include it. So for a moment, I will turn off my screen. Right. Okay, I am adding numericals. Kindly wait. So please wait. I'm adding the numericals to PPT. So just one more minute. Okay, now I'll share the screen once again so that we can solve the remaining numericals. I hope it is visible to all of you. Okay, so just now we have solved this numerical. We'll go to the next one. Okay. So an amount of 100 kilowatt of heat is transferred through a wall in steady state. One side of wall is maintained at 127 degrees Celsius and the other side is at 27 degrees Celsius. The entropy generated due to the heat transfer to the wall. So here in this case, we have to calculate the total heat generated due or entropy generated during the process. So I'll draw a figure for your understanding. So there is a wall. Wait. What should be straight? So this is a wall, okay? What they are saying is the one side of the wall is at 127, other side is at 27. So this is, let us say this is 127 degrees Celsius. This is at 27 degrees Celsius. Inside of the wall, there may be bricks, etc. Material will be there. Okay. So this is the wall, and there are bricks, and on that bricks we have a plaster. Very common example. So amount of heat transfer here it is 100 kilowatt. That means 100 kilojoule per second heat is transferring from this side to this side. Here we have to calculate total entropy of generation. Okay. Okay. Right. Now see here, the formula for entropy change is S2 minus S1 will be equal to integration dq by T plus S generation. Okay. Now see here, they have mentioned that heat transfer is steady state. What is meant by steady state? That means this value will be constant for longer duration. These values will not change with respect to time. Steady state means the values or the variables will not change with respect to time. So in this case, this system is under steady state. So for the steady state, the changing entropy is actually 0. This S2 minus S1 is 0. There is no change in entropy due to steady state. Only there will be entropy generation. So here this, due to, for steady state we can say this term is 0 will be equal to integration dq by T plus S gen. Now what is dq by T is here? That is Q1 or Q1 divided by T1 plus Q2 divided by T2 plus S generation. Now see here, Q1 and Q2 is same, that is 100 kilowatt. So 100 kilowatt I will convert into watts, 10 to power 3 divided by 127. Now I will convert this 127 into Kelvin. So it will become 400 Kelvin, and this will become 300 Kelvin. So this will be equal to 400 and plus 100 into 10 to power 3 divided by how much? 300 plus S generation. Okay. This side it will be 0 because the system is on the steady state. The variables are not changing with respect to time. So now can you calculate? Yes, can you calculate? Okay, so this is integration 1 to 2, and this will be, sorry, this will be Q1 minus Q2. Okay, so let us say this is under 1, this is side is 2. We are taking integration 1 to 2, and this will be Q1 minus, so here it will be minus sign, right? I hope it is correct, because see in this case, this side will absorb the heat is being absorbed, and this side the heat is released. Okay, so heat absorbed is always positive, heat release is always negative. So this will be Q1 will be positive and Q2 will be negative. Even though the values are same, the sign conventions will be different. Okay, so calculate S generation. Very classic example is this: heat transport through wall. We have to calculate the entropy generation. And there is the integration dq by T. Previously we have taken sorry, so Q1 by Q, T1 plus Q2 by T2 plus entropy generation. But in this case, Q1 is positive because Q1 is heat absorbed and Q2 is heat release, so that is negative. Even though magnitude is same, the sign conventions will be different. 83.33. Okay, so 83.33. So this is joule or kilojoule. What is the unit? I think it is joule per Kelvin. This is unit of entropy, joule per Kelvin. So see here, this value is positive and entropy generation is always positive. So wait, entropy generation is always positive. So value is coming 83.30, right? I will again explain. There was a wall. The heat transfer was taking place 100 kilowatt. One side was at 400 Kelvin. Another side was at 300 Kelvin. We have to calculate entropy generation. What is the formula for entropy? S2 minus S1 integration dq by t plus H generation. But as the system is under steady state, that means values are not changing with respect to time. So you can say this side will be 0 and this side will be equal to integration dq by t, and this comes out to be 83.30. Okay. Now let us solve some numericals based on second law. Okay. For practice purpose, as I promised, I will take a practice of this numericals. Right. So these are related to second law of thermodynamics, or what we have studied yesterday. All it is related to that. Next example, a condenser of a refrigeration system rejects heat at rate of 120 kilowatt, while the compressor consumes power of 30 kilowatt. Coefficient of performance of the system should be. Okay. So don't get scared, sir. You are not taught us refrigeration system. You are not taught us what is condenser, what is compressor. It is not related to that. It is just simply related to a refrigerator, right? So condenser of refrigeration system rejects heat at 120 kilowatt and compressor consumes 30 kilowatt. So if I draw schematic of a refrigerator, so this is a source, this is a refrigerator, this is a sink. Okay, it is at TL, this is at TH. What refrigerator does? It consumes external power W, it takes the heat from sink and it rejects the heat to the source. Here source is condenser and here power is consumed by compressor. Okay, so what they are saying is that compressor power is 30 kilowatt and condenser is rejecting 120 kilowatt. Okay, so in this case they have given QH, they have given W. You have to just calculate COP. What is the COP of refrigerator? The QL divided by W. Or we can say, yes, okay. Now how to calculate QL? We know W is equal to QH minus QL. Okay. In this case, W is given, that is 30 is equal to 120 minus QL. So QL will be equal to how much? 120 minus 30, that will be 90 kilowatt. Okay. Now simply I can calculate COP of refrigerator will be equal to 90 kilowatt divided by 30 kilowatt. So this will be equal to 3. Okay. So COP of the refrigerator in this case is 3. As simple as it is. And the option number D is correct. Okay. So write it down. Okay. Now let us take next example. I hope everybody is clear about this example. Okay. The heat removal rate from a refrigerator speed and power input to the compressor are 7.2 kilowatt and 1.8 kilowatt respectively. The coefficient of performance of the refrigerator is, okay. So for this example, I will just draw the schematic. Rest calculations you have to do. So again, this is a source, which is at TH. There is a fridge or a refrigerator R. Then there is a sink is there, which is at TL. It will consume W amount of work. It will extract QL amount of heat. It will release QH amount of heat to the source. What they are given here, heat removal rate. That means QL is given. In this case, that is 7.2 kilowatt. And the compressor power is given, that is 1.8 kilowatt. That is external work done on the system. Heat extracted is nothing but the refrigeration effect, or here in this case it is QL. You have to calculate the COP. What is the COP of refrigerator? QL divided by W. So calculate and tell me the answer. Yes, calculate the COP. How much it will be? Okay, so it will be 7.2 divided by 1.8 18 so it will be 4. Next numerical we'll take. So 4 is the correct answer. Those who are still solving, 4 is the correct answer. Next is 3.45. Okay, so this is a numerical number. A reversible cycle receives 40 kilojoule of heat from one heat source and temperature of 127 and 37 kilojoule from another heat source 97 degrees Celsius. The heat rejected to the heat sink at 47 degrees Celsius is. So very interesting problem here. We have two heat sources and one heat sink. So this is let us say it is a heat sink is there. Oh, sorry, heat engine is there. It receives heat from two sources. So this is again TH1, this is TH2, this is QH1, this is QH2, and it will do some work obviously, and it will reject equal amount of work to the sink at TL. So it says that it receives 40 kilojoule. So this is 40 kilojoule from the source which is at 127 degrees Celsius. So this is at 127 degrees Celsius. It receives 37 kilojoule from another source which is at 97 degrees Celsius. Heat rejected to the heat sink is at 47 degrees Celsius. So heat sink is at 47 degrees Celsius. Now see here, I will write down the given values. TH1 is 127 degrees Celsius. If I want to convert it into Kelvin, I have to add 273. So that will become 400 Kelvin. QH1 is equal to how much? 40 kilojoule. TH2 here it is 97 degrees Celsius. If I want to convert it into Kelvin, plus 273. So this will become how much? 280 plus 90. 370 Kelvin. And TL is given 47 degrees Celsius. Again converted to Kelvin, this will become 280 plus 40, that will become 320 Kelvin. Okay. Yes. Okay. Now see here, they have given it is a reversible cycle. For reversible cycle, we can apply the equation integration, cyclic integration dq by t equal to 0 for reversible cycle. So it will be equal to q1 divided by th1 plus q2, sorry, qh1 plus qh2 divided by th2 plus ql divided by TL will be equal to 0. All the heat interaction, entropy interactions will be equal to 0. So I will put the values here. 40 10 to power 3 divided by TH1, that is 400, plus QH2 is how much? 37. 37 into 10 to power 3 divided by TH2 is 370, plus QL is unknown, we have to calculate, divided by 47, that is 320 Kelvin equal to 0. So from this calculate QL. Can you calculate? Or if I'm jumping too much, I will do step by step. So this will come out to be how much? 100 plus this will come out to be how much? Again 100 plus QL divided by 320 will be equal to 0. So this will become QL equal to, this will become 100 minus here, minus 100 minus 200 into 320. So this will become, I think, 64 into 10 to power 3 minus 64 to 10 to power 3, or we can say minus 64 kilojoule. Okay. So if they have asked you only value in this case, if they are saying heat rejected, okay, so it is assumed that it is minus. Okay, if they are saying heat rejected, you should write only 64 kilojoule. Okay, if they are asking you the value of QL, then you can write minus 64 kilojoule. Okay, but if they are asking you only heat rejected, so it is actually assumed that it is a heat loss, it will be negative. So you have to write just only 64 kilojoule. Okay. So here QL will be 64 kilojoule. So I hope you have understood the concept here of Clausius inequality. For reversible cycle, the equation is integration dq by t equal to 0. For irreversible, we have equation, we have just solved it, that is S2 minus S1 is equal to integration dq by t plus S generation. Okay. Now I will take a last example and then we can stop. So for a moment, I will stop the share so that I can copy the numerical. Okay, so this is the last example of today. A heat pump absorbs 10 kilowatt of heat from outside environment at 250 Kelvin while absorbing, it absorbs from outside environment at 250 while absorbing 20 kilowatt of work. It delivers the heat to a room that must be kept warm at 300 Kelvin. The coefficient of the performance of the heat pump is. Okay. So may I ask what is the difference between heat pump and refrigerator? Let us see how many of you remember from last lecture. What is the difference between a heat pump and a refrigerator? Yes, does anybody remember what is the difference between heat pump and refrigerator? So if you see the cycle, I will draw the cycle of heat pump, right? This is TH, this is, let us say, heat pump, this is TL. It will absorb QL amount of heat, it will consume work W, it will transfer the heat QH. Now if you see this diagram is same for heat pump and refrigerator. Okay, the difference between heat pump and refrigerator is in its objective. Objective of heat pump is to maintain this source at higher temperatures. Okay, so that is the objective of heat pump. Objective of refrigerator will be to maintain, wait, let me change the color, to maintain the sink at lower temperature. So that is the objective of refrigerator. Okay, Now, what they have given in this case is, let us write down. So it absorbs 10 kilowatt. So absorb means this is a 10 kilowatt, which is at 250 Kelvin. So this is at 250 Kelvin. It consumes 15 kilowatt of work, and this room has to be kept at 300 Kelvin. Okay. So a heat pump is usually used in European countries. That is why we are not hearing its name. आपल्याकडे ते वापरतच नाही, त्यामुळे आपल्याला माहित नाहीये. पण हे टीम पंप फार पॉप्युलर आहे युरोपियन कंट्रीज मध्ये. तिथं त्यांचं टेम्परेचर फार कमी जातं. त्या केसमध्ये त्यांना रूमचं किंवा बिल्डिंगचं टेम्परेचर मेंटेन करायचं असतं एका सर्टन व्हॅल्यूला. त्या केसमध्ये ते काय करतात, हीट पंप वापरतात. So it has to be maintained at 300 Kelvin. Now here we have to calculate the COP. Okay, what is the COP of heat pump? Here it will be different. It will be QH divided by W. Now QH is unknown. It will be equal to work plus QL. Okay. So work is 15 plus 10. So this will become 25 kilowatt, right? So COP of heat pump will be equal to 25 divided by W is 15. Calculate. So COP has calculated by Shubham, I think 1.67. So this will become 1.67. I hope it is correct, Shubham. Yes, okay. So COP of the heat pump will be 1.67. So this is a very classic question which is asked in the interviews or the external examinations. What is the difference between heat pump and refrigerator? So that you can tell them that heat pump's objective is to maintain the source at higher temperatures. The objective of refrigerator is to maintain the temperature of sink at lower temperatures. Okay. Calculation COP is very easy part, as you may have seen. So write down this. So write it down. Okay. I hope everybody has got the same answer, right? So let us move to the last part of the entropy, and then we can finish this concept of entropy today. So it is related to the entropy change for some of the processes, right? So we'll try to cover that. So the title here, it is entropy change for processes. Okay, so there are some standard formulas are there. So first case here, it is for gases. What is the entropy change for the gases? Now, what is the specialty of gases? In gases, we have two specific heat, that is Cp and Cv. This is specific heat at constant pressure. This is specific heat at constant volume. Okay, so I'll just write down the formulas for your reference. So S2 minus S1, changing entropy is equal to Cv ln natural log T2 by T1 plus R natural log V2 by V1, or it is Cp log T2 by T1 minus R log P2 by P. Okay. So write it down. For gases, change in entropy, these equations are there. S2 minus S1 will be equal to this much. And this is per mass. Okay. If you want to calculate into mass terms, you have to multiply by mass. All this unit here it is joule per kg Kelvin. This is a unit here for entropy. I will check if we have some numericals for this. Okay. So I will take this numerical and then we can solve it. So for gases, the formula is this, right? So there are other changes also taking place, like let us say for phase change, right? For phase change processes, right? Anybody know what is phase change process? So we have three phases, that is solid phase, liquid phase, and gaseous phase, right? So if you see the chart for the phase change, many of you might be already knowing. Let us say temperature versus volume chart is there. Let us say we have ice, which is at, let us say, initially minus 10 degrees Celsius. Here we have ice, right? When I will increase the heat, it will be like this. Say temperature versus enthalpy I will take. And it will reach to some point. This is 0.0 degrees Celsius. At 0 degrees Celsius, what will happen? This solid ice will be converted into liquid water, but there will be some phase change process will take place, and this is the latent heat of solidification is added. By adding latent heat, it is converted into liquid water. Now again I will increase the temperature, it will reach a certain temperature. Now this temperature here, we already know boiling point of water is 100 degrees Celsius. At boiling point also, again I have to supply a latent heat, so that is latent heat of vaporization, and then again this will be converted into vapor water or steam. Again I can increase the temperature of steam. In this case, let us say this is again reverse entropy. The change in entropy for the phase change process will be equal to the entropy of liquid minus entropy of solid here, and in this case the change in entropy in the latent or the phase change will be entropy of vapor minus entropy of liquid. Okay, so it is as simple as it is. We have to take the difference between the entropies. Okay, so this is a phase change process. So there are many of the cases are there, applications are there where we have to find out the entropy change. Okay, so quickly I will take one numerical, I will add to the slide and then we can stop. Okay, wait, just last numerical we are going to take. I'm transferring that file. Okay. Okay, copy. Right. So here I will add. Yes. I'll share the screen. Let us solve the last numerical of the day. So it says 1 kg of air, that is gas, its gas constant is given, undergoes an irreversible process between equilibrium state 1. The conditions are given 20 degrees Celsius and 0.9 meter cube. And equilibrium state 2, that is 20 degrees Celsius and 0.6 meter cube. The change in entropy of the system is okay. So here the formula is already there, as you might have seen. Will be equal to CV log T2 by T1 plus R log V2 by V1. Now in this case, they have given the volumes, right? So that is why I have taken this formula. If the pressure values were given, I would have used the second formula. What is the second formula? Cp log T2 by T1 minus R log P2 by P1. Now in this case, they have given the volume. So that is why I am going to take the first formula. So S2 minus S1 will be equal to CV. What is the CV for air? The Cp value for air, it is 1.005 kilojoule per kg Kelvin. The CV value for air, it is 0.718 kilojoule per kg Kelvin. So I'll write down the formula here. 0.718 into log T2 by T1. What is the temperature value? It is 20. So T1 is equal to T2 is equal to 20 degrees Celsius. If I want to convert this into Kelvin, this will be 293 Kelvin. Okay. So 293 divided by 293 plus log value here it is, or R value is 287 into log V2 by V1, right? What is the V1 in this case? V1 is 0.9 meter cube and V2 in this case it is 0.6 meter cube. Okay, so what is the V2 by V1? 0.6. State 1 is this, state 2 is 0.6. So divided by 0.1, right? So can you calculate the total change in entropy? See, again, log of 1 is 0. So this will be 1, log of 1 is 0. So this whole term will be equal to 0. You have to just calculate 287 into log 0.6 divided by 0.9. So calculate this one, and this will be the value of the change in entropy. Yes, what will the value here of entropy change? Minus 116.38. Okay, minus 116.38. So this will be in joule per kg Kelvin. Okay, see here the entropy is decreasing, so this is a changing entropy is negative. Okay, changing entropy is different concept, entropy generation is different concept. Often student gets confused between this. Entropy generation is different concept, changing entropy is different concept. Changing entropy means स्टेट 1 टू आणि स्टेट 1 आणि स्टेट 2 मध्ये जे चेंज होते त्यातले एंट्रोपी चेंज आहे. एंट्रोपी जनरेशन हे नेहमी पॉझिटिव्ह राहणार आहे, बट एंट्रोपी change can be positive and negative. So here entropy change is negative, but entropy generation, this term will be always greater than equal to 0. You will always remember this. This is different term and this is different term. So with this entropy concept or the part of this first chapter is completed. In next chapter or in next lecture, we'll cover the last point of first chapter, that is first law for chemically reacting systems, right? In which we'll see some of the chemical reactions. We will try to calculate standard enthalpy of formation, standard enthalpy of combustion, standard enthalpy of the reaction, etc., etc. So these are some terms are there. So we have to calculate the enthalpy values for a given chemical reaction, and we have to apply the first law in that case. So in next lecture we'll cover that part also, and within this week the first chapter will be completed. I will release assignment number 1. Very good examples are there in assignment number 1. You try to solve it afterwards, right? If anybody is facing any problem up to this part, they can ask. Quickly I will cover what we have learned today about the entropy. We started with Cauchy's inequality, that is integration dq by t as well less than equal to 0. For reversible process it is equal to 0. For irreversible it is less than 0. For processes we have equation integration ds will be always greater than integration dq by t, and this reduces to this equation s2 minus s1 will be equal to integration dq by t plus h generation. H generation is entropy of generation, which is always greater than or equal to 0. It is equal to 0 for reversible. It is greater than 0 for irreversible. As all the processes in the universe are irreversible, the entropy of the universe is continuously increasing. Right? Then we have applied this equation for some of the processes. First, we applied for the gases. So these are the two equations for the gases. Then we can calculate similarly for the phase change. How to calculate for phase change, that we'll see in chapter number 2. Then we have solved some numericals related to entropy, right? Where we have applied the formulas. This example was related to irreversible processes. We have solved the for cyclic also, right? last numerical was related to entropy change for the gases, right? So with this, we'll stop today. Please enter your attendance in the chat box. Enter only number. Yes. So with this, we'll stop. We'll see in next lecture.